constructor theory isn't limited to the parochial properties of quantum theory. It emerged from quantum theory, but it emerged from problems in quantum theory. But it's a level of description, and I'm gesticulating as if it was a higher level, but actually it's a lower level of description than quantum theory. It's more reductionist than quantum theory, and yet it is more compatible with emergent properties. We're hoping eventually that things like knowledge and economics, ultimately consciousness maybe, though my own view is that consciousness will require an extra idea, not just elaborating ideas from within constructor theory. It requires an idea, another idea, at least one.
Hitherto, the line from Newton through to Einstein and then to quantum theory has been ever more difficult and elaborate mathematics. And so then string theory comes along. And this, I think, leads to the general opinion that the next theory of physics will be more mathematically challenging, and hence all the reasons earlier that maybe we won't be able to understand it. But constructor theory seems to have echoes of that famous Feynman line where he said that perhaps the ultimate laws of physics, or whatever he meant by that, would be more like the rules of the checkerboard than some fancy dynamical mathematical laws. Is that what you have in mind with constructor theory, some checkerboard type notion of possible and impossible moves?
Yeah, it could be just like that. You can't understand if you have a listing of all the moves in a game of chess. You can't understand what's happening there unless you know the rules of chess. But knowing the rules of chess, the people who make chess programs think that if you know the rules of chess, you can understand all the games, but not true. If you want to win games as opposed to just win them, then you need a lot more than just the rules. And yeah, constructor theory is just like that. We hope.
But it's more than just physics, as you say. This is an explanation that's not merely about fundamental laws of physics, but is extendable into biology and...
Yeah, or you could say that physics is going to consume all those fields, just like it has consumed many other fields. We think of constructor theory as a theory of physics. And if it consumes those fields, and that's what physics has always done.
Okay, can I back up for a second on constructor theory? Because I think it's the part that might be understood the least by the general audience. I know that Chiara wrote a book on it. You have not yet written extensively for the lay people on it. What problem are you trying to solve? And where are you at so far? And what level of confidence do you have that this is the right approach to go down?
Oh, those are very long questions.
It's okay. I think the answers are illuminating.
So when I wrote my first paper on constructor theory, which was a philosophical paper, didn't have really any physics. It was published in a philosophical journal. And I wanted to explain what we were trying to do, what this research program is, because we didn't know at the time, and we still don't, what the definitives of constructor theory are going to be. We're going to find those as we find the applications. So I thought I would give some motivation. We don't have a good theory of initial conditions. Think carefully, why should we need initial conditions when we are perfectly fine to have no theory of the final conditions? So that's one thing. And then the thermodynamics thing. And then there's the fact that things like computation and information can't be expressed in the initial conditions plus laws of motion way. And I thought I would write a quick paper, and I ended up with 18 motivations. I can't think now, and you can look up the paper if you want to see all 18. I can't think what they all were now, but this seemed to me a motivation for thinking that this constructor theoretic approach was a very simple change in worldview in a certain way. You can say very quickly what the change is, but the ramifications are huge, and it seems to touch all these problems in different fields. And that's what motivated me to try to make a theory out of this. And the next thing that happened was that I gave a talk at the Clarendon Laboratory, and Chiara was in the audience. She was a graduate student working on quantum information. And she came up to me afterwards and said, what about, so that can't be right, can it? Because and I had indeed contradicted myself in the talk. And so then she came round and we chatted about it. And I said, do you want to work on it? Because there's a lot more to work on than one person can do, especially me. So she said yes. And since then, she's worked on the constructor theory of life, constructor theory of probability, which are in a way translating existing theories into constructor theoretic form and uncovering little nuggets. My favorite nugget is that in constructor theoretic thermodynamics, first law is to do with information, not just the second law. So the way she defines the first law is similar to statistical mechanics, but you end up with the first law that's about you can do this and not that, you can do this and not that, and as a result you get the version of the first law, but better than normal because it incidentally has the property that let me see if I get this right. I think it incidentally has the property that there must be a lower bound on the energy. Whereas existing thermodynamics doesn't. You have to put that in as an extra axiom. And if there were no lower bound, then you could have an object that you were just extracting energy out of without violating the second law, just first law, extracting energy forever. And that would make a perpetual motion machine of the first kind. With the existing thermodynamics, you have to impose that as an extra condition. In constructor theory, you don't have to. Meanwhile, we have together been working on the constructor theory of time. Yeah, perhaps I could say something about the constructor theory of time. Really, the first people to have this idea were Wheeler and DeWitt, who trying to find a viable theory of quantum gravity, and they found a theory of quantum gravity in which there's no time. Time doesn't appear in the theory. There's just different spaces, three-dimensional spaces, which all have amplitudes, quantum mechanical amplitudes, and they all exist simultaneously. And time is an emergent property of the way they are entangled with each other, but nothing ever changes. It's just an emergent property of how they're entangled. And then, as Julian Barber made a big thing out of it, wrote a whole book about it, then so that was a theory tied to general relativity. It would only work in the context of general relativity. Page and Wouters made a construction that will work in any quantum theory, not just quantum theory of gravity, but any quantum theory. You can formulate a theory of time that doesn't have things changing in it, and so that the static universe still has time because of entanglement. So that is more general. It doesn't require Wheeler and DeWitt's specific theory of space-time. And when I saw Page and Wouters' theory, I immediately thought, yeah, this is it. This is what time is. And then many people have tried to get something more out of it, and they failed. And then Sam came along and got something more out of it. So he's got the most advanced theory of time in the universe, in the multiverse or whatever so far. In a way, it's only a small improvement on Page and Wouters, but it is more general, and that's what we want. And then Chiara and I are working on constructor theory of time, which we hope will be this kind of, for the moment, the ultimate version of that, which instead of deriving the concepts from some theory, like quantum theory, it lays down rules that it says any theory that obeys these rules will have time. And Chiara already did that with probability. So that any theory that obeys these rules will have probability, even though there's no stochastic processes. So it has probability in the sense that quantum theory does, that an observer, a rational observer, will bet in certain ways, but nothing can happen in everything's deterministic. Constructor theory, by the way, is necessarily deterministic. It can't work unless everything's deterministic.
But your view of the quantum multiverse was already deterministic.
Yes. So quantum multiverse obeys that rule. And I've also written that the prevailing concept of a stochastic theory that just doesn't make sense. It's like saying that something's more probable is like saying it has more magic. It's not. Nothing follows from that statement. You need an extra theory to make sense of that statement. Yeah, and now I'm working on the universal constructor.
Is universal constructor related a little bit to your talk in Fabric of Reality about virtual reality generators?
So that's an interesting thought. I don't think it's related, except in the general way that the fact that there is such a thing as virtual reality, that you can make a virtual reality machine in our universe and that it can simulate anything, then that's Turing universality or computational universality. That's in constructor theory, you hardly have to say that. Like it's so built in that it is the most natural thing. You'd have to work very hard and get over some very difficult obstacles if that weren't true in constructor theory.
So far in constructor theory, you've basically got some better or more universal explanations of existing theories. When do we start getting predictions? When do we start getting tests?
So I guess having a lower bound for the energy is a prediction. Not a very strong prediction, but because everyone believed that already. I think that where constructor theory will start making where people will start formulating theories about new things within the constructor theory framework, that will be when these new things combine existing theories where it was unexpected before. Now, I don't believe in the quantum theory of life, for example. I think that's a dead end and blind alley. But that sort of thing is the sort of thing that constructor theory could provide a framework for that existing theories don't have a framework for. It's a pity. It's like I thought in Fabric of Reality, I thought that the multiverse kind of solved the problem of free will. I didn't quite say that there, but I hinted that maybe it solves the problem of free will, and I don't think it does at all. But even though it doesn't solve it, it gives a framework in which one can think because free will involves counterfactuals have much more meaning in theory of the multiverse than they do in a Newtonian or classical theory. And in constructor theory, they have even more meaning. That's the kind of thing. I can't foretell the growth of knowledge. I don't even know that constructor theory is going to work. It could end up as a kind of curiosity that this is what people in the early 21st century, some people thought would illuminate things, but it only provides a little bit of illumination. And now we know what the real illumination is. We don't need it. That might be, or it might be the opposite.
This is a meta question. I don't want to take us off on a tangent, but you just said there, as a good Popperian would, that constructor theory could be completely wrong and it will just be a footnote in the history of physics. There are other people out there with new theories as well. They do not speak in a Popperian way, and they will say about their new theory that they're holding up that this is going to solve the origins of life, this is going to tell us what the nature of time is, this is going to solve what the preconditions of the Big Bang were, and so on, with great confidence. And they, I have to say, get a lot more attention, and they get the investment, and they appear on some big podcasts and things. Is this an inherent disadvantage of being a Popperian, that we couch our terms in such conjectural language?
I suppose if you were fanatical about getting approval and funding, and then you would maximize that. But I think people working on things, usually the people working on things, deep things for their own sake, for the sake of those things, are the ones that tend to make progress. In some cases that will make them famous, like if you invent mRNA vaccine, then it'll make you famous. Though those people weren't famous before. And I think I'm always suspicious when someone says what they're going to invent or what they're going to prove or what they're going to find. I would rather they said, this is a problem I'm going to address. I don't know where it's going. Here's my problem. We find it interesting. We think it might do so, but maybe it won't. Maybe it'll do something we haven't thought of. I find that more attractive as a stance. Like when I'm thinking of someone else's elevator pitch. I think Popper used to say, what is your problem? What is what are you working on? And that in research, when you meet someone who is not in your field, the first thing you say is, what are you working on? That's not what are you going to find. That would be a weird question.
This is a little historical, and I know you don't necessarily like to go into your own thought process because we're not here to copy you, but I think it is illuminating to think about the connection you made between physics and computation. You basically have created or helped create the quantum theory of computation. And there are a lot of researchers and technologists now working on quantum computers, tons of them. In fact, we just talked to Maria. She's off to work at some quantum computing company.
Yes.
And not all of these people believe in the quantum theory of the multiverse. Did you start with Hugh Everett's many worlds theory and then get to quantum computation?
Yeah.
Or was that, and do you view that as fundamental? Like, how can you explain quantum computation with the observer collapse theory, or is that just contradictory?
As you may know, when I first came up with the idea of quantum computer, I didn't even think of it as a quantum computer. I didn't call it that. What I was trying to do is, so the consensus at the time among people who work on Everett's multiverse theory was that the multiverse theory gives the same experimental predictions as collapse theory. And in a way that was already known to be false. There's the paradox of Wigner's friend. But you know how people just take paradoxes, yeah, that's a paradox. They don't think that's a reason why we're wrong. It's fundamentally wrong in our worldview. So I thought that Everett's theory must be testable, and it was testable because it proposed the different dynamics from the wave function collapse, all the wave function collapse theories. So I thought, okay, how would we test it? And I thought, simplest thing, you do a version of the two-slit experiment, then you have to have a measurement of that measurement. And how do you do that? And I thought, oh, it could be done with a computer. So there's this computer but if the computer is going to have quantum, the two-slit experiment, or whatever you call it, the Stern-Gerlach experiment, or whatever, they're all equivalent, really. If it's going to have that in it, then the computer can't be decoherent. So it can't be a classical computer. So it must be augmented with these quantum operations. Which operations would you need? So I added some operations to make a coherent classical computer with these extra operations. And that's what it was in my mind. It was just an object. It was an object connected to a computer with certain, that what I was interested in is something else. It was this experiment that you could do. So then I wrote a paper about that experiment, which among other things, there was only one section of the paper that had that in it. And then that paper was rejected, and the story that they said that's philosophy. And I was like, okay, yeah, I don't care. So I put it aside, and I didn't get it out again. I would tell people about it. Like when I was talking to other physicists, I told Roger Penrose, and I said, okay, now you've got to accept that if quantum theory is true, universally true, then Everett is right. And he said, yeah, but quantum theory isn't true. Okay, that's a consistent position, but that's not the position that the vast majority of physicists took. So then at the same conference where I asked Roger Penrose that, I was also talking to someone who worked for a publisher, and he said, why don't you submit it? And I was like, oh, it's too much trouble. And eventually I submitted it, and it was eventually published at the same time as my Universal Quantum Computers paper, even though it came much earlier. And people think that I thought of them in the opposite order, but I didn't. I first thought of the experiment to test Everett, and then much later thought about quantum computers.
Is this the same experiment that's mentioned at the beginning of Infinity as going inside the mind of the AI?
Yes.
I see. So you came up with that first.
Yes.
So you had to create experiment to test many worlds, and it said, okay, is the observer making a difference?
Yes.
Let's get inside the observer.
Yes.
But if we get inside the observer, it's just a double slit experiment all over
Yes.
again. Unless there's a different kind of computer than the classical computer, it's not going to be affected by the same interference effects that the double slit experiment is vulnerable to. So we need to create qubits or quantum computing or what?
Yeah,
like,
again,
yeah.
the term qubit wasn't invented till much
Sure,
later.
okay.
And I did, as I said, I didn't think of it like that.
Okay, so you were solving a different problem.
Yeah, a different
Related.
problem, and it didn't cross my mind that this was a new mode of computation.
And to do this test, we'll need AGI as well.
Yeah, that's not my fault.
Exactly.
It's the opposition that wants the conscious observer to do something different. Okay, and in that case, you put a conscious observer.
It needs AGI and it needs quantum computing. It needs both.
Yes,
The AGI has to be a quantum computer internally.
it has to be running on a quantum
I see.
computer.
Because the alternative perspective is,
Otherwise, you have interference.
well, yeah, it's the opposition that is saying that it is the observer collapsing the wave function. And so, well, if that's their position, then we have to have an observer that can observe things without collapsing wave functions.
Yeah, but this observer doesn't do much that's quantum. He only does a few quantum operations, like half a dozen quantum operations. But most of the time, he's thinking about things like, do I know this, and so on. And that's all done with classical operations, but done with coherent quantum objects. So they have to be done with qubits instead of bits. Yeah, so in relation to what we were saying before, I would never have said at the time, I'm going to invent quantum computers. It didn't occur to me. Even when I finally did, I wasn't even trying to do that. I I had this conversation with Charlie Bennett, where he said, the complexity, and I said complexity is arbitrary because it depends on the hardware. And he said, but the hardware is physics. So I said, okay, if the hardware is physics, then you're using the wrong physics. So I thought I would go home and recast Turing's analysis in quantum physics instead of with paper tape like he did. And then I saw that there were algorithms that didn't have classical analog.